Okay, so it's a couple of minutes past 2 now, so should we get started? Thank you everyone for joining this live demonstration of EBSD today. We will be presenting this as part of the EBSD users group here at the University of Manchester in the UK. Today's presenters will be myself, Alec Davis, Jack Donoghue, who's on the Preuss microscope that we'll be using today, and Alec Gholinia will be assisting us as well. Yeah, just for the few of you that have joined, just to reiterate, please do mute your microphones during the presentation, and do bear in mind that this session is being recorded, so if you don't want to appear in the video, please do turn off your cameras. So just a bit about us. We're a group of academics, postdoctoral researchers and experimental officers that are working together to try and put forward some good EBSD demonstrations and live presentations. Last year we put on quite a few of them, with Ali leading the charge there. Thank you very much for that, Ali. You can get details of everything that's happening with this group at the website microscopy.manchester.ac.uk/EBSD. On this site we have the up and coming EBSD users meeting, so this one is us today, the 30th of September. Just going forward, we're planning on doing another one of these demonstrations with a bit more of the more technical detail. But also on this website is some information about how you can join the EBSD users group. We've got some information about some software, and it documents all the past meetings that we've had and all the past presentations. We also have a Slack group, which has information like that as well. So if you were to join the EBSD users group, you'll be invited to join that Slack group as well. So this is why we're here today. Electron backscatter diffraction, or EBSD. Now, Ali very kindly gave a presentation last year going through a lot of the theory and the more complicated bits and pieces of EBSD. And we're not going to go through all of that today, but we are going to give a quick overview of the main bits and pieces. So this is a standard EBSD setup in an SEM chamber. So what we have is a technique to measure crystal orientations in the SEM and map phase distributions. And we do this by simply attaching our EBSD camera to the side of the chamber. We have our sample tilted here, and we'll go through a bit later the importance of tilting. Our electron beam hits our sample. We get backscattered electrons that come out of the sample and hit this phosphorus screen on the detector. And this converts the diffracted electrons into light, where we can now see this pattern, and it's collected by the EBSD camera. And then by rastering the electron beam, we can collect a map of information, whether that be phases or crystal orientations or both. This is a list of all of the equipment that we use at the University of Manchester. Now, first I should mention that all of our equipment is produced by Oxford Instruments. So a lot of the software-based stuff that we'll be doing today will be based around Oxford Instruments software and their systems. Now, we have 3 different sets of detectors at University of Manchester. We have the older CCD cameras. So we've got the Nautilus S and the Nautilus Nano, and these are on our microscopes such as the Sirian and the Quinta 650. These are high sensitivity detectors, and they give good high spatial resolution. They have a maximum speed of 140 hertz. And when I say this, this means that the rates that they're collecting EBSD patterns, so the maximum here is about 140 patterns per second. And the resolution of this camera is 1344 by 1040. And then we've got a slightly modified version of the Nautilus, which is the Nautilus Max 2. Now, this is a high-speed detector, so it sacrifices sensitivity, so we can collect patterns much more quickly. And this is quite well suited for in situ experiments. For example, Jack and I have run some experiments on our Nova system, which is equipped with this camera, using an in situ heating stage, so we can collect patterns quickly as we're increasing and dropping in temperature. And you'll see that the resolution of this camera is much lower, and that's to get that speed much higher. And now we move on to the new generation of detectors, which are the symmetry detectors. These are CMOS rather than CCD detectors. And these have very high pattern resolution modes, and they can achieve amazing speeds over 3000 Hertz, which is really quite incredible. And the resolution of these is 1244 by 1024, so it's similar to the Nautilus Nano and Nautilus S. Right, so this is just a summary of all the microscopes and EBSD systems we have at the University of Manchester. We've included the Aztec versions here of the software. So Aztec is Oxford Instruments acquisition software for EBSD. You can see that they're quite varied at the moment, but we're in the process of updating everything to version 6 when we get our hands on it. So our current latest version we have is on is 5.1 or 5.0. Now, to note, these are the 3 different buildings. So we have the MSS bunker. So all of these microscopes will soon be moved over to the MECD building. We have these 2 in the mill and this equipment in the Photon Science Institute. And you'll notice that we have a lot more symmetries at PSI. And that's because the equipment here is just much more specialized and it's for specific experiments. Today, we'll be using the thermoscientific Aprio SEM, and the one we have here is specifically designed for high throughput EBSD. I think that's my next slide. There you go. It's just a picture of the chamber that Jack, the room that Jack is now sitting in. So this is the Aprio SEM. We've got our symmetry detector bolted to the side here, and we've got 2 PCs, one for the microscope and one for the Aztec acquisition software. And when we move on to the demonstration, I'll be switching the view between these 2 PCs on the live stream so everyone can see what we're doing. Just to mention why we're using this particular SEM, as I said, it's well set up for EBSD, but also we've set this one up for live streaming. So it makes the perfect SEM for this demonstration today. We should also tell you what sample we're using. So we'll be using a titanium dissimilar weld sample. Now this is effectively 2 different alloys welded together. So one side we have Ti64, and then the other side we have this Ti5553 or Ti5553. Now for those of you who aren't familiar with titanium, in these types of alloys, which are the most commonly used alloys, you'll find 2 phases present. You'll have the cubic beta phase, which is shown in this orientation map at the top. And then you have the hexagonal alpha phase in between, which is shown in this bottom map, again, an orientation map. Now, the thing to notice is that the beta phase is all one single orientation. And this is useful for us for this demonstration. The other thing to note is that in the Ti64, the beta phase is very small. So we've only got about 5 volume percent here. But in the 5553, we have about 50% beta. Now, what becomes important is that because the alpha and the beta phases in this material on the 5553, because they're so well interwoven at a nanoscale, this affects how our EBSD patterns behave. But on the Ti64, we're mostly just scanning the hexagonal phase. So we get much stronger patterns. So the key thing to note is that we get different strengths of patterns and the way it behaves and the electrons interact with the material. And the last thing I want to mention about this sample is that I polished this not very well, and I did it 6 months ago. So we wanted to use this sample because we didn't want people thinking that we were using, you know, a perfect silicon sample. So that's why we were getting good patterns and really strong signals. We wanted to use something that was a bit more realistic for everyday experiments, just to show that all of these things are possible, even if the sample isn't the best. Okay, so here is the EBSD setup again. And I'm about to show, flip over to Jack to show you this in the chamber. But this is a different view from what I showed before, because I want to point out 2 very key things here. So we have our sample tilted. This is our tilt angle here. Normally we tilt to 70 degrees, but this is not something you have to use. You can change that, and we'll get to that later. But I have 2 parameters to define here. So one is the working distance, and that is the distance from the pole piece, or where your electron source, and the focal point on the sample. And then we have the detector distance, which is the distance from the focal point to the EBSD camera screen. And one last thing to mention, we need to talk about the EBSD pattern center, because this has become important throughout this presentation. So the key concept is that we want to convey, talking about the pattern center, is that it needs to be known accurately for reliable crystal orientation indexing. If your pattern center is not accurate, you may have a drop off in indexing of your orientations. So we need the pattern center to be aligned or positioned correctly on the camera screen. And we define the pattern center as the normal on the phosphorus screen, which you can see here. And that is, the normal is supposed to hit the focal point on the sample. But what we need to do is define the coordinates in our SEM chamber. So for the acquisition coordinates, which in Aztec is defined as CS1, we have the X is the horizontal direction, Y is the vertical direction on your sample, and X comes out of the sample onto the pattern center screen. And you can define a separate sample coordinate system as well, which is defined as CS0. You don't have to do this, but if you do wish to change these coordinates, you can apply a rotation in Aztec software if you choose to. The pattern center is defined in the acquisition coordinate system, CS1. And this means that we have an X coordinate in the horizontal, a Y coordinate in the vertical, and then the Z coordinate is defined as the distance from the pattern center to the focal point. Okay, so now I'm going to hopefully move over to Jack. Okay. So hopefully you can all see the SEM screen here.
Yeah, I think that's... Yes.
Oh, now we're on the Aztec.
My camera recording has already failed. Okay, I've got a backup, don't worry. Okay, so before we start doing anything, we need to start thinking about where your sample is positioned before you put it in the chamber. So we've got a couple of tips. First is to avoid pre-tilts. Try tilting the stage rather than using a pre-tilted sample holder. So if you have slight misalignment in the rotation of your pre-tilt, for example, in our Quinta 650 system, then you can get distortion and dropping off of indexing. Stub extenders are very helpful, which you can see on the screen here, which we've used today. And this just helps put some distance between the stage and the pole piece to give you a bit more movement in your sample chamber. For multi-stage holders, like you can see here, and this is again like on our perhaps the test scan large chamber system, you want to put the sample in the farthest position from the camera to again avoid the stage hitting the pole piece. And the third thing that I think we're going to show today, Jack, over to you.
Yeah, right, so I've already got it set up. As you can see, the detector is inserted. We are at 70 degrees tilt, which is a pretty standard tilt position. I'm working at 20 kV to begin with, which is a good starting point with EBSD, and I am chucking a load of probe current down there. We're at 51 nanoamps, partly just to help these patterns zing for kind of showing this off. And first of all, I'm going to show kind of centering the diffraction on the camera and the Z height. So we're currently at a working distance of 9 millimeters. I don't know if Alec, if you want to show off what's happening on the phosphor screen.
Yeah, certainly can. Give me 2 seconds. Yeah, go ahead.
Cool. I'm just waiting for you to update, which hopefully it will come soon. Yeah, so there we are. That's the live pattern we're getting at the moment. I'm at fairly low magnification. And this is in the single crystal region. So we're getting a very strong pattern. As Alec was saying, the pattern center and the diffraction on the screen, you can see the raw diffraction on this screen here. and this is the one with various backgrounds and things applied, and the pattern is quite high up on the phosphor screen. The pattern center, which is represented by this green arrow, is a bit too close to the top of the phosphor screen for my liking. So one of the things that we have to play with is the working distance. So to bring that pattern center further down, we can increase the working distance. These are well-tested moves that I'm doing in quick moves. Don't try this at home. Do these things in slow, careful movements, but I have practiced all of these positions. So we are going from a working distance of 9 millimeters to 13 millimeters. Whoa. And you can see that now the pattern center is far better positioned on the screen, and the diffracted signal is far more evenly over the phosphor screen. And we can take this to the other limit. So I'm now going down to 19 millimeters working distance. And now we're in the opposite situation to we were at short working distance. You can see there is a lot more noise over the top of the signal, and all the bands are concentrated at the bottom, and our pattern center is quite far down. You may wonder why you would, well, generally, if you're doing a single field mapping, you would always try and optimize the position of that diffracted signal. Why you might want to go to 19 millimeters can be demonstrated by going to full screen here. Do you want to just maximize that a second?
Yeah.
So I'm currently near the top of the sample.
Go ahead.
Yep. So as you can see in this top left-hand quadrant, this is one edge of the sample, and you can see our position in the beam. At a longer working distance, this 19 millimeters working distance, I am able to do EBSD over the entirety of the sample, which I would not be able to do at a shorter working distance. However, as we have already covered, the pattern center is a little bit low. An advantage of these newer symmetry detectors over the Nautilus detectors is we have another degree of freedom to play with in order for positioning our diffracted signal. It's not just about working distance. I can also, change the height of the detector itself. So currently our pattern center is a little bit low, but we can move the detector down. So I'm going to do this in a series of small steps of 2 millimeters. And you can see we're getting much better pattern on the phosphor screen. Maybe one more. That's probably a little bit too high, but gives you the idea that we have this extra degree of freedom. So we would now still be able to do the whole sample with our pattern center optimized. Just going to return it to the position it was and go back to position. One other thing that we have to play with, we all get very used to working around at 70 degrees, but it isn't hard and fast with the rules. It is a very good kind of compromise position, but we can work at a range of tilts. So if you watch the diffraction pattern here, we're currently at 70 degrees tilt. If I go to 60, again, don't try this at home. You can see the band contrast lessens. We're getting less diffracted signal onto the phosphor screen, but it is still very much possible to do EBSD. These patterns would still be indexed, and much like the previous example, working at a longer working distance, I am able to do the entirety of the sample at 60 degrees tilt, nicely gliding past the pole piece.
Jack, can you just maximize that quadrant just so we can see it a bit better?
Yeah, not that quadrant, that quadrant. So now at 60 degrees, because the angle of this pole piece is 60 degrees, I'm able to slide past the pole piece.
By the way, we're not getting a pattern because Jack is actually scanning now. So we only get a pattern when we have the beam in a certain position on a single point. Yeah.
Although with this being a single grain, I can be quite high mag in order to get that. Let me just go back to this position here. So here that's back at 70 degrees. And likewise, being able to go down to 60, we can increase the tilt. So I'm now going to take the stage up to 80 degrees tilt. Excellent. I shall maximize this one again. And it continues that the amount of signal we're getting has increased. Yeah, so the contrast in the bands has increased. A benefit of working at 80 degrees is that you do have a much shallower depth of interaction, but you do lose a bit of resolution in Y. And as you can probably see from that screen, our freedom to move around the sample is next to non-existent. I would not want to move around due to the risk of hitting into the pole piece. Right.
Also, as a further note on that, not many SEMs can actually go to 80-degree tilts. Some of them are restricted, so do be aware of the limitations of the stage movement in the microscope you're using.
Yep.
Do we want to talk about the different types of Z and tilts? Because we skipped over that a little bit.
Yeah, can do. So on this one, let me just go back to my safe position. Yeah.
I'll maximize the SEM screen for this. Yep.
Yeah, so in the university, we have two main different types of tilt stage. One where Z will always remain true, or pure Z. Just trying to think of a way to show that on here, but no. Which are like the test scans, the Zeiss instruments, where if you move in Z, your region of interest will always stay the same because you are moving purely up and down. Then a number of our other stages, mainly on the FEI systems, Thermo Fisher, the Z is linked to the tilt. So as you tilt, if you move in Z, it will move in and out and you gain a component of Y. This is that latter type of stage, so you have to be a little bit more careful, a little bit harder for setting up for EBSD. And these newer stages have something called the ZY link, or compucentric Z, which will move the Y to take account of that shift as you move in Z. Is that it?
Yeah, can you just show us quickly, just change a couple of positions on there, Jack, just to show.
Yeah, I just want to do that a
for
little bit with, to be safe, I'm just going to take out the detector a bit.
So this is where, you know, where we have the microscope, where Jack is saying the Z is actually on the tilt. So as you're changing Z, it depends on what tilt you're on.
So if I go from this 9 millimeters working distance down to 19 millimeters working distance, you see it moves back in Y first and then comes down in Z. I'll do the reverse of it now, go back up to 9 millimeters working distance, goes up in Z. Oh, that did it simultaneously, so it wasn't so obvious. So back in Y, down in Z. Or no, the other way around.
Back in Z, down in Y.
Yeah.
And we do just have a list here of all the microscopes. Again, just a summary table to show you which one does which. So it tends to be these systems here that have the CompuZ functionality, and then it is very much split between the different manufacturers with the other ones. Okay. Do we have anything else to add from that, Jack, Ali? Or should we move on? So we need to talk about beam conditions for collecting scans. So the two main ones to consider are voltage and current. So if you have a high current and a high voltage, you have a large interaction volume in your material. And what this gives you is a very fast speed because you're getting more backscattered electrons. But because of the large interaction volume, you're reducing the resolution you can achieve with your scans. And this is particularly important, like in these titanium two-phase alloys, where you want to get the phase separation of the nanoscale material. If your current is high and your voltage is high, you're going to struggle to do that. And it's also a case for using lower currents and lower voltages if you have charging or beam sensitive samples. Now, we've got a couple of things to demonstrate for the difference that the change in voltage and a change in current causes. And for that, I need both screens. Hold on 2 seconds while I change things again. Okay. So what we'd like to show you is the difference between high voltage and low voltage and the change in the Kikuchi pattern that we get. So hopefully we can.
Yeah, no, we'll go, first of all, we'll go for a nice high voltage pattern. I'm going to go up to 30 kV. It'll take a few seconds. So there is a 30 kV pattern. And now if I'm going to drop the kV down to 10 kV, again, take a little while for it to change the accelerating voltage. Now I'm going to try and find that pattern again. Oh,
same grain rather, yeah.
Yeah. Yeah, there we are.
Yeah, well done.
Nice.
So yeah, what we have is broader bands because we've got lower voltage in the current one where it's live on the right hand side. So we have lower interaction volume, so it gives us better resolution, but our signal is lower because we have lower interaction volume, but also as our bands are wider. So there's, if you can see that it's almost harder to see the bands as sharply as the 30 kV. So the indexing won't be as optimal to give us the orientation, but the resolution will be higher. So there's a price for everything. So we gain in resolution, but we lose in signal and also the ability to index. So 30 kV is a good bet. If you have a large grain size, you don't worry about resolution. You choose 30 kV and you get better indexing.
And we should also think about those poor people who don't work on lovely metal. Sometimes they will have to use the low kVs and the lower probe currents, whereas we can get away with 30 kV. Maybe not everyone can. Right, I'm going to get rid of that and go back to 20 kV, and we'll just do a little bit of a show on the effect that the probe current has. Again, it is a variable for you to play around with, find out what works best for you. Generally, again, so the patterns are looking good again. The probe current, again, with charging samples and things, but also about resolution. You can generally focus a smaller probe current a lot better than you can a large probe current. So in order to show the effect of probe current, I'm going to use what Aztec now calls restore default. On the older versions of Aztec, it's called auto exposure, and I much prefer that term. Admittedly, what it's doing with the CMOS detector it is a little different to what it was doing with the CCDs, but auto exposure is roughly what it's doing. It will go through a range of different exposure times and find the one that maximizes the signal to noise on the detector. So I'm going to turn, up until now I've had frame averaging on, we'll go over that later, but that's just to make these patterns pop a bit more. So I'm going to hit auto exposure at 51 nanoamps, which again is a lot of probe current, and you wouldn't necessarily always be doing that. But at 51 nanoamps, using the auto exposure, I don't know if these numbers have come out particularly large on your screen, but it's come up with an exposure time of 1.77, and the detector feels it can go at around about 560 hertz in these conditions. If I drop the probe current down, and I'm going to go down to from 51 down to 1.6, which is a probe current that is a reasonable, around about a nanoamp is a good starting point on a Nautilus Nano, I would say. In the region of kind of 1 to 5 nanoamps is usually a good place to start.
Yep.
So we're now down, yep, the aperture has changed. So I'm going to hit restore default auto exposure one more time. And we've gone from an exposure time of 1.77 to 54.7. And you can see the pattern quality is still very similar if not better, than what we had at the high probe current, but we are having to expose for that much longer. So yeah, we are now going 18 hertz opposed to 500 hertz. I'm just going to go back up to the mega current one more time to show something else off. So again, we're just changing aperture.
So these numbers are in milliseconds. So 1 millisecond means 1,000 patterns per second.
Yeah.
So, yeah.
1,000 captured patterns per second, not necessarily indexed patterns per second. Right, so we're back up here. I'm going to restore default. So it's come up with 540 hertz, and that is maximizing the signal across the phosphor screen. And you can see those patterns look nice. The software will have no difficulty indexing those. But it isn't a hard and fast rule that just because auto exposure has come up with a number, that's the number you have to use. Aztec gives us these buttons above and below the restore default number, this frame time. And if you click those, it will halve or double the time. So we're at 1.84 and 540 hertz. One click of these, we're now at 0.919 milliseconds and 1,000 hertz. And still, the patterns aren't bad. I am pretty sure that Aztec would not struggle to index those patterns if given the right kind of settings. And we could perhaps go even faster. So now, we're in speed 1 mode. So yeah, we've hit our maximum speed. So yeah,
just to say a point that what you're looking at on the right-hand side is the raw pattern, and then with background correction, you get the middle one where it's live. It's enhanced pattern.
This is the enhanced.
Yeah,
the one. Yeah, this is the enhanced. Yeah. Raw looks like this.
Yeah, the same one. That's right.
Yeah. This box also is not. This box can be typed in, so you can decide the exposure time that you want. This is a little bit different on the Nautilus detectors. These buttons are still available to you, but they're where we have a kind of infinitely dividable or infinitely settable frame time to a certain degree on the symmetry detectors. On the Nautilus detectors, they are far more discrete values, and you should really work for maximizing your exposure time within those kind of set values.
Yeah, and so what Jack shows very nicely, so restore default, what it does is maximizes the signal on the raw pattern just below the saturation. So the saturation is when it gets so bright that basically we can't see anything. So that's the maximum sort of frame time or exposure time. And then you can drop below that sort of really nice intensity on the screen. You can drop below that and it still have a good enough enhanced image for the indexing to happen and get indexing. Yeah.
Jack, do you want to just show speed 2 and how if you hit restore default, you can actually make it go a lot faster just by manually entering a different exposure time?
Yeah,
so here Jack is just dropping the pixel resolution of the pattern to make the detector faster with speed 2.
Yeah, so it's come out with 1.84, but I'm pretty sure, and that runs out at 540 hertz, so very similar to the last one. And I can take that down to 0.3 maybe, and be getting over 3,000 hertz. The patterns aren't fantastic, but they are there. So we can potentially run at 3,000 hertz. Right, so do we want to go over some of the settings now? Is that the plan?
Yes. We're a bit short on time, but we might have to run over a little because of the technical difficulties.
Right.
So first we need to look at backgrounds on our camera image. So one of the defaults that's selected when you open Aztec is the auto background. And that's just what Jack's been showing between the raw patterns and the corrected patterns. So that is usually worth doing because it gives you stronger patterns and it helps the software to index the patterns, but it does slow your acquisition down.
Or it can.
It can, yeah. Especially if you're going very fast.
Well, with more binning, essentially. In speed 2, when you've got more pixels, speed 1, sorry, and sensitivity, it will slow things down because it's far more processor heavy when you've got a larger image to do it on.
Yeah, okay. And the second background we've got is the static background. And this is to help remove the things that obstruct the camera getting the patterns. So on most detectors, there's usually a few small bits of dirt on the camera.
Yeah, I've just made this bigger to highlight them. You can see a few here.
And because these are on the camera screen, these are always going to be there. So you can actually collect a static pattern of this to correct for it, which you can do during setup. And you would usually collect around 100 frames. You don't usually need more than that. And this will help just clean up, as you can see, those spots have removed.
Yeah. When setting the static background, try to include as many grain orientations as possible.
Oh,
so
yeah.
In a large grain material, zoom out as far as you can in order to collect as many orientations, because you do not want to get one orientation stuck in the background, which then will be taken away from the patterns and you won't index that orientation.
Yeah.
So you don't want to etch a pattern into the background while you're taking it. Just a couple of questions have come up while we're discussing these topics. Kieran asks, does dropping the pixel resolution affect the quality of the EBSD map? The pixel resolution, if you of the pattern, if you drop it, then it goes faster. But then if you don't have enough quality of bands, they fail to or have struggle to index the patterns because you can't pick the bands. So higher pixel resolution does give you better indexing, but you lose time, of course. And then David asks if he's about frame time. So you're going to be talking about frame averaging, right? So we can talk about that a little bit. So he's saying, is sacrifice reducing frame time to increase speed is dependent on the accuracy of solution required, therefore local misorientation across a grain. So he's talking about if we frame average, I guess, the patterns, what effect that will have.
Well, we can do that. So here is a nice pattern. We've got no frame averaging on at the moment, and it's a little trickier for you to see with the refresh rate going on there. But if we do some frame averaging, I've just gone up to 3 frame averaging. Was that noticeably different? I might have to up it a bit to really show it off. You would never normally go up to 10 frame averaging. I'm just showing the effect that it has in reducing the noise, making this, and you can see the difference in the signal to noise ratio, hopefully. Down at 1, no, it didn't actually change that much.
Yeah, so while we're talking signal to noise ratio, we should also explain gain. So the gain function amplifies the camera signal before it's converted to a digital signal. So if you've got noise, gain is going to exacerbate it. So you need to take that in consideration when choosing which gain you have. So when you're using high binning, gain needs to be low, and when low binning is used, gain can be increased. I don't know if we can demonstrate that easily with the...
Not easily, but it does allow you to run a bit faster.
Yeah. Okay.
So when you increase the frame, if you decrease the frame time, then you get less signal. Then you may want to use a higher gain, but then you'll get higher noise. So then if you have a very poor pattern, you may not want to do that if you have also very small patterns. But larger patterns, good quality patterns, you can use higher gains if you're using less frame time. If you're using less frame time, your speed goes up, but you lose signal and indexing. Yeah.
So should we move on to the solver as we're running out of time?
Yeah. So the first thing to look for is the band detection area.
So that's over here.
It's rare that you'd need to change this, but it's always worth checking when you first open Aztec. Because if someone has changed it, it will save where it was last left, even if it's been closed. So what you want to do is usually you're going to maximize it and centralize it, so you collect as much of the bands as possible. But say if you had something shadowing, say you've got something in the corner of your detector screen, you want to tell Aztec to ignore that part of the pattern because it's going to interfere with its feature extraction software. So what you would do is just shrink the pattern, the collection region a bit, and move it out of the way of that shadowing. But it's usually you won't need to do any of this, but it's worth just checking over it every time you set up an EBSD. So I've put here in my notes that we should have a quick discussion about separating out the exposure time and the frequency of patterns that it's collecting on the previous tab, and then what we're adding by processing these patterns and indexing them. So there's always an additional cycle time, which you can see just below the pattern detection screen here. It says cycle time analysis. So at the moment we're adding 0.6 milliseconds. So this is always worth considering as well, because we're going to be changing how we index the patterns to best optimize speed and accuracy of your indexing. So first, it's probably worth discussing the different acquisition modes, which is in the settings tab on the top right. For later versions of Aztec, we have different names for things that we did in the older versions. So I'll go through them quickly one by one. Optimized band detection, or BD, which relates to optimized TKD in the older versions of Aztec. This is the best to use in most cases. It has some clever indexing algorithms, and it gives a good compromise between speed and indexing rate. You also have the standard BD and what was called the optimized EBSD. So this has some good uses, which we might go through in some later talks. But the difference is that it can detect the band edges as well as the centers of the bands. And then finally, the last one is refined accuracy. So this does an extra refinement to get a better fit to your patterns. It's got a really high angular resolution, so this is less than 0.1 degrees. So this is good to use if you need to be really careful about the orientations that you're detecting. The next setting down is the bands, the number of bands. So this is what you're telling the software to look for, how many bands that you're telling the software to consider when it's solving the pattern. And again, it's a trade-off of speed and better accuracy. So if you look for less bands, you're using less processing, so it runs faster. But you could potentially get poor indexing, especially in multi-phase materials like titanium here. If you have more bands, it runs slower, but it's more accurate. But 11 is a good place to start. Now, we've actually got a table here. Hopefully you can still see that. So we've got this band detection guide here. So what you need to be aware of is that by setting Aztec to detect a certain number of bands, it's going to require a certain number of bands to be detected before it will index a pattern. So for example, if we're indexing 7 to 11 bands, if we've told it to do this number, then it has to identify 6 or more bands before it will find an orientation solution. So it's worth noting and need to be careful about that. Right, and then the last thing on that tab is Hough space resolution. So I won't go into the details of Hough space, but essentially what you're doing is the Hough space translation will change the inclination and the position of the bands, and then position them as points on a two-dimensional space, which Jack has just brought up on the left-hand side. And your Hough space resolution changes the resolution of this translated pattern. Now, the things to be aware of with this is, again, if you're running high resolution Hough space, it's going to slow down your speed. And if you're running lower Hough space resolution, you can run faster. But the things to be wary of is you don't need a Hough space resolution higher than your pattern resolution, because the way they convert is that your Hough space resolution is half that of the detected pattern. And again, we've got another table just to show. So for instance, if you're running on speed 2, you've got a 156 by 128 resolution of pattern. So 156 divided by 2 is 77. So you don't need anything higher than that. But actually, for speed 2, running, you know, between 30, just 30 to 40 is fine, but you can go up to 60 or it's a case of choosing what's appropriate. But just be aware that if you're got a very low resolution of pattern that you're collecting, you just don't need a higher Hough resolution because you're not adding anything. I think that's the point to consider there. But if you want to make the most out of things, you need to be, you know, paying attention to which Hough space you're selecting. Do you want to add anything on that, Ali?
Yeah, I just want to say that what you said was perfectly correct, but just want to add that the Hough resolution shouldn't normally be higher than your pattern resolution. It's just a waste of resources of the computation time. So if you have, for example, 156 pattern resolution speed 2, your Hough space shouldn't be more than 77, because actually what it does is it's double that plus 1, the actual Hough resolution that it uses. So it becomes so anything below 77, but it's even for that is too much. So what you said is correct. So to get the best kind of speed against resolution, sort of compromise to use something like 30 or 40 for speed 2. Yeah.
Okay. And the final thing that you'll want to do on this tab is to refine your solution. So we've got this little plus button here above the solutions tab. If you select that, this will calibrate the pattern center using the detector distance and the working distance, which are those two parameters that I showed you earlier on the EBSD setup. Now, the important thing to remember here is that you need one high resolution pattern for one phase only, because what you're doing is you are more accurately defining your pattern center with the detector distance and working distance. So it's not actually dependent on the phase or the orientation that your beam is currently interacting with. What's important is that you get a strong, reliable pattern to do this on. And that brings us around to what we consider to be the best procedure for pattern optimization in all of these steps. So intuitively, you would go through these tabs one by one, but actually it's good to get up to this stage with a really strong pattern. So we're talking, we want to go into resolution mode. So we've got a high resolution of pattern that we're detecting. We want a high frame averaging, so we get a really nice pattern. And then we want to get the backgrounds sorted for that as well. So we're giving the computer the best chance of getting the best solution to the EBSD pattern that we have. So Jack's just showing you that now. So he's gone to sensitivity mode.
Yeah, sensitivity is pretty good for getting a good pattern. It doesn't need to be resolution.
Yeah.
But we really do struggle in this sample. I said include enough grains. There isn't a position on this sample with that doesn't have this prior beta orientation in it. So it does make this a bit tricky to get a good background.
Do you want to move to the single phase region quickly?
That's not an awful lot better.
Oh, isn't it? Ah, shame.
We're in the single phase region.
Oh, are we? Oh dear.
Yeah. So I can collect one, but it's going to have a lot of marks in it from the actual patterns. But yeah, so yeah, we can see probably, oh yeah, horrible shadowing. But yeah, anyway, we can get a very nice pattern.
And then we move along to the optimized solver. So we've got, we're on band detection 11?
I have gone to number of bands 12, and the Hough resolution is actually through the roof, so it's at 100. But we can see that it is, yeah,
Picking things out nicely.
picking the peaks out nicely. Actually, on this system, and since I've been playing with this today, it is very close. So I don't think this is going to make an enormous difference. But then, so we refine based on this position on a very nice pattern. And it's making a slight difference to the detector distance, ever so slight distances, slight distance to the working distance, and we accept it. And what you're really looking for here is for these bands to really snap to what your eye can see. Now, unfortunately, as a demonstration goes, this is already pretty good. So the calibration for this system is better than I've seen on a lot of microscopes. And that just happens to be the case. But I calibrate it and you do see it's snapping to these bands a bit. If I maximize that a bit, I don't know, if I take off the refinement, you can see, especially along this band here, the 1, 2 bar 1, if you can see that's a few millimeters off, and then I apply the solution refinement, and it really snaps to those bands. And that's what you're looking for from a good fit.
Yeah. Correct. And also, when you're refining, what you're looking for is to bring the MAD down, so mean angular deviation. So it was around 0.2, and when you refined it, it just fell below 0.2. So that's 0.2 degrees. So that shows that it's just, you know, you've refined it and it's managing to accurately index. Yeah.
Yeah. So in your setup stage, once you've done this, if you want to run, say you want to run a really fast map, you can now go back to the optimize pattern tab and then select whichever mode you want. Should we say speed 2 for this?
Yeah. Well, let's very quickly, with a few minutes remaining, set up a map. So I won't start a new project. I did want to, just to drill into people. When you start a new project, please change the name. The number of things I've seen around the university, how many project ones there are in existence. Please give it a new
At
name.
least I have 50, I guess. Sorry about
that. So as we work through, go into specimen geometry. Alec touched on this earlier. So this is where you can put in a specific geometry and it will take 90 away from the Euler angles, add 90. If you know your TD, RD, ND. Personally, I always work with it in 0, 0, 0, and I know my sample. Depending on the work you're doing, you might want to use these. I learned today that MTechs, I think, particularly likes this button to be pressed. But at the very least, go on to this page and check that the one you're expecting to be ticked is ticked. Otherwise, your orientations will not make sense to you. Double check the phases are the correct phases that you're looking for. And double check that these tilts look sensible, that somebody hasn't ticked a pre-tilt when you're not using a pre-tilt or vice versa. Take an image. I'm going to collect a Fonseca.
While you're doing that, I'll just say that the sample coordinate systems can be, after you've acquired, can be rotated. The data can be rotated to the different sample coordinate systems, but the acquisition coordinate system will remain as it is. That won't be touched in the data set. Yeah.
So we've already optimized the pattern. So I'm now going, speed 2. These look glorious, but this is running incredibly slowly. We're going to get rid of this frame averaging. The restore default auto exposure is coming out at 1.6, but I know I can run faster than that. I'm going to tell it that maybe we could go at 0.3. And again, they look pretty good. I'm going to push the symmetry to what it can do. So go down to 0.26. And we're going to be getting around about 3,600 hertz out of it, potentially. We don't have a background applied, so I am just going to turn off that. There is a pattern in the background, unfortunately. Let's just collect that. Right.
If you can't get a static background, just turn that off and use auto background. If, for example, you're looking at really large grains and it's impossible to get a static background.
Yeah,
now,
particularly when they're
running in speed something mode, speed 2 mode, it is coming out with a reasonable MAD, but we are using 12 bands still, which is going to take far too long because, as Alec was saying, it's going to be looking to fit 7 bands, and that's far more computationally heavy. So that will slow down the process. You can see down here that the cycle time, so the processing, the indexing of the pattern is taking longer, the exposure time. So you will end up dropping quite a bit of speed. So I'm going to go down to 11 bands. 11 bands, and the Hough space doesn't need to be nearly that high. In fact, if it was that high, you are oversampling. So I'm going to drop it down to, let's say, 30. I mean, I think it still indexes reasonably. Our MAD has jumped up a bit, but we will get that back in speed. And then finally, we will go to acquire map data. Unfortunately, the most useful place way to collect this has been moved down here. It's not open as default. We select the region we want to do a map on. I'm going to go over that. We can select a suitable step size. So you don't want too many points across a grain.
Yeah, so just a couple of notes on this. If you want to do something like Jack's doing here and just sample a microstructure and look at the specific details, then a small step size is probably your best bet, because you want to resolve the morphologies and the features. But if you're trying to collect a texture analysis, then you only need like a few points per grain, but you want to be indexing thousands of grains to make sure that you've got a proper texture statistical data set to get it correct.
It's correct. So typically you want minimum of 10 patterns, 10 pixels across a grain if you want to get the grain size, for example, or morphology of the grains. But in a texture component, if you just want to analyze texture, you don't need that much. Can you also click on settings, please, Jack, there before you start?
Yeah.
Oh, okay.
So I've started it, but yes, I can.
Yeah. So there you can also store patterns. So
yeah, actually, before I say this, because I saw that question pop up.
Yeah.
So you can store the patterns.
Yeah.
One reason why you might not store the patterns, so I'm going to collect over this area again. So this is only a tiny map. It will be completed in, it thinks 1 minute 37. We'll come back to that. If I say I'm going to store the patterns, and yes, those settings are fine, and I hit start, we will get a warning. And so even though this is a very small map in the grand scheme of things, this will take up 7 gigabytes of memory to store the patterns.
And so that's with low resolution patterns.
Yeah, these are very low resolution patterns. If you're doing this with high resolution patterns, it is easy to get a single map running into the hundreds of gigabytes. So yes, you can store the patterns, and with proper use, please do, but you have to be careful with your data sets and removing them from the Oxford PCs afterwards.
Because it's a wonderful way to work, but yes, please manage your data sets very well, because what you can do is you can take the data set offline and re-index it as much as you like in your own time, adjusting the settings.
Yeah. A couple of other things about just on this collecting your map region. You should be careful about running long maps or anything really collecting slowly, so under sort of 100 patterns per second, because you're going to end up with significant drift. So maybe not an issue if you're doing a bulk texture scan. But if you're trying to do something like we're doing here, then you may end up with a significant amount of drift and you won't be collecting your EBSD map correctly, or at least be aware of what's going to happen. So you can get significant drift below about a 1/4 micron, but if you're going fast, you can get away with a 50 nanometer step size if you're over, say, 100 patterns per second. But these values are very current and voltage dependent, because you're changing, the amount of electrons that are interacting with the material, and that's going to change the amount of drift. And do be aware as well that it depends a lot on the material that you're trying to map, because some materials charge a lot more than others. And the final thing that I think we should probably show is compare the exposure time and the speed that it's saying that it can collect the patterns. But when you add the processing time, you can see the actual speed that it's collecting with those two things combined here. So we showed that it was saying 3,600 to collect the patterns.
3,600, and in fact we were indexing at 2,942. Still no slouch, but not the stated speed.
And you using what background correction here?
That was with both.
Both. So you can get that back if you, for example, switch off the auto background correction there.
But yeah, that has its own risks. You can't do that at low magnification. You can't do that. So yeah.
Okay. Alec, have you been monitoring questions?
Yes, I think we've answered most of them. So you've covered the saving patterns. I mean, I think, David, we've covered your frame time. So yes, by increasing the frame time, you increase the speed, but then you lose sort of indexing percentage, possibly, depending on your pattern quality. So one question's come from Ellie, an extra question is, what is a good MAD? So that's a good question, and it has the software, the global limit is 1.3 degrees. So the MAD is the mean angular deviation between the angle of the bands that have been detected and the indexed solution. So how far are they? How far is the indexed bands to the detected bands? And that's shown as MAD. And 1.3 is the global limit, but it depends on your pattern resolution, right? How well can you pick out those bands? And something like anything below 1 degree is very good. And for high angular resolution, you want to get those down to very low values, to 0.2, 0.1, by using really high resolution patterns. So if you use refined accuracy, that actually refines the indexing. So you can use a sort of get away by using a Hough of 50 even with refined accuracy, but then it goes back to the pattern. And if you're using a high resolution pattern, it slows down the system even more, but you can get below 0.1 degree angular resolution there. So that's how, I hope that answers your question there. There are some materials like copper, Miri asks, like copper, nickel, that are quite similar. So I have trouble detecting them separately. Good question. What's there to do? Jack,
that's what we're going to be covering in a future talk. That's one of our next topics.
That's right. So there's quite a few ways we can do this, Maria. One is using the EDS signal, for example, to separate them. The other one is we have phase separation. So because of the lattice parameter difference, we can pick out the differences. So there's a few ways, and we can cover that as a special session for that. But EDS is a good way for very similar.
If anyone has any samples that they want to suggest to demonstrate those two particular features, that would be good as well. Just so, because we can go away and find some samples that work well for that, but it might be a bit more useful if people have something particular that they'd like to demonstrate. If you've got any suggestions, please do. So
Maria, if you have a copper and nickel sample that you want to discriminate between the two, send them to Alec, and if you polish them well, and we can try and cover it for the next session. Fan, yes, below 1 MAD is good, so it's correct. Could you please show page 8 in the slides again, Lou? I don't know, Lou asks, I don't know why he wants that, but can you show that?
Yeah, already on screen.
Okay, right, I think he wants to get a snapshot of it or something. So Elliot says, yes, thank you, Lou, thank you. Okay, those are the questions. I think we've covered all of them. Have we got anything else? I think we've covered Kieran's questions as well, I guess. Dropping the pixel resolution affects the EBSD quality, map quality. So pixel resolution of the pattern will give you higher pixel resolution, gives you high angular resolution, whereas you get slower maps. Whereas if you use smaller patterns, you get faster map indexing, but you lose in angular resolution and quality. Is there anything else? I think, oh, yeah, there's another one here. Josh says, could you please repeat where this recording will be available? And perhaps put a link to it.
So the plan is to, well, first I need to edit out the bit where my computer crashed. But then we're planning on maybe putting this on YouTube. And then the link will be shared around. If not, it will go as a Dropbox link on the Slack site.
Yeah, I think initially we're going to have it as Slack site, on the Slack site, definitely. So please, if you're not a member, become a member so you can have access to it. Royce have also raised interest, Henry Royce, to house these training videos. So before we put it on YouTube, we need to talk to Royce Institute, because they'll probably help us to also, we may get them edited by the e-learning and then put them on ROI. So we will let you know for the future how publicly they'll be available. But if you remember, you can just...
Yeah, I think the raw recording will be fine to just go up on the Slack site, I think.
Yeah,
that should be fine.
Is there anything else there? Okay.
Do we have Sorry, go on, Ali.
Zuleika asks, is it possible for organic crystals? No, that's a good question. Very good question. So organic crystals are usually high, long-range order. And so the pattern, and also very small crystals. So, and they're also affected by the beam. So getting a pattern from these is difficult. I've not seen one, but it's always, I don't know if Jack and Alec have had experience with these sort of things, ever come across them?
I have
but
not.
Yeah. These things, you can see them in possibly in TM patterns from them, but to get any Kikuchi patterns, you need shorter range order, and I have struggled to see any patterns over the years from these kind of samples. So if you have a good candidate, maybe it's worth putting it in a microscope and having a look, but usually they are not possible. Kieran says, thanks. Fan, do we have recommended, Fan asks, do we have a recommended walking distance and detector distance for Aprio? I guess that's for Jack.
No.
Sorry, Alex,
Well, the point is that you don't want to be, so if I'm teaching someone to use the Aprio, I will give them some suggested starting points for working distance and detector distances, but it's different for every sample size, every different scan, different tilts, different currents, different voltages. It's always going to change. I think that's the key point to take away. But the thing is, when you're considering these, so for working distance, you always want to be considering, where is my sample going to move when I tilt it? Is it going to be near the pole piece? Is it too close if I move it towards the bottom of the sample? And similarly, if it's a lower tilt, is the bottom of the sample going to hit the EBSD detector? These are the things you want to be considering when moving your sample around. So if you've got a very small sample, I would recommend a short working distance. But if you've got a very large sample, then you'll need to use a larger working distance to make sure you can move it around.
And be adaptive. Look at the pattern, see that pattern like we did here and go, yeah, you know what, the pattern looks a little bit low. If the pattern looks a little bit low, bring it up. Yeah.
So it's correct. So first of all, safety, make sure you don't break the system. And secondly, what you're looking for better resolution, you want to shorten the working distance. Shorter the working distance, you get higher resolution and also stability. As you move down, if you have a larger working distance, you get more instability in the beam. So that's what you're looking for. But as you work at a shorter working distance, safety becomes more compromised. Bear that in mind. Okay. Is there anything else there? No. So I guess that's it. But generally, I would say to start with, just to finish up, start with, use basic settings that is comfortable and safe, and then you can experiment going to other settings. Like working distance, anything between 10 and 20 is usually quite good resolution for most samples.
But there are more gains to be had through people using the right solver settings, I think, than by playing around with geometries. If you're struggling with your EBSD, I think there is a lot more you can do with both your pattern capture settings and your solver settings. So hopefully from this talk, you can go back, look at those slides, play around a little bit with those numbers. There's no risk to the microscope if you change your Hough resolution or change the number of bands you're looking at. And I almost guarantee that you will see an improvement when you work on those settings.
Yeah. Really good. I think is everyone happy? Are there any other questions?
I can't see any more questions.
It's nearly 3:20 now, so if anyone does have any follow-up questions, please do post them on the Slack site and we'll try and answer them as quickly as possible. Yeah. We've currently got another session like this planned for end of October, but that's not confirmed yet. It may get pushed to November. depending on how much time we need to prepare it. But we'll keep everyone apprised of what's going to happen. Jack, Ali, do you have anything to add?
I just want to say thank you to Jack and Alec to make this live session so interesting, and also, you know, setting it up. I know with a bit of technical difficulty, but it's not an easy task, you know, to make sure that we cover the bits that we want with the right equipment and make sure that it works during the day. So thank you for your efforts, Jack and Alec.
Thanks, Ali. Okay, well, thanks for everyone for attending, and I guess we'll see you soon. Cheers.
Cool. Thanks, everyone. Goodbye.
Bye-bye.
Thank you. Bye-bye.
Thank you.